Alright, we want to talk about chemical equilibrium. So chemical equilibrium, we said, is attained when opposing reactions are proceeding at the same rate. So the rate at which the reactants forms the product is equal to the rate at which the products produces the reactant. So when we have this condition, we call it chemical equilibrium. So equilibrium mixture is possible because the reaction is reversible. So forward reaction is equal to backward reaction. So you see this all right, we see nitrogen tetraoxide, and then it produces nitrogen dioxide. Basically, you see the forward reaction, and then we see the backward reaction as well. So the backward reaction produces N2O4, and the forward reaction produces 2NO. So we see 2 moles of NO2, and then we see 1 mole of N2O4. All right. So the rate of forward reaction is reaction constant is N2O4, and then we have rate of reverse reaction or backward reaction KRNO2 raised to power 2. Remember, so whenever you see that kind of bracket, it basically stands for concentration. Okay, so at equilibrium, we see that forward reaction equals backward reaction. So as the equilibrium constant in terms of what concentration. So we are looking at the equilibrium constant, and then we said it's always for the Haber process. We have something like this. So the Haber process is one of the processes that is very common in chemistry. So we have 3H2 plus N2. N2 is nitrogen, and hydrogen reacts to form ammonia, right? Production of ammonia. The equilibrium constant is Kc in terms of concentration. Remember, NH3 raised to power 2, basically because the product flux then all over what the reactants. Okay, so here is the moles, right? 2 moles. Then for the H2 we have 3 moles. Basically, that's it. So we have pressure, and we say the constant pressure. We have pressure of the product all over pressure of the reactant. That's basically what it is. So using from ideal gas law, we have PV equal to nRT. So P will be equal to N over V times RV. N over V, remember, is moles, right? Number of moles. Basically, you can actually put it that way. The relationship between Kp and Kc, we have Kp will be equal to Kc concentration of RT raised to power the mole difference, right? This is some of the coefficient of the product minus some of the coefficient of the reactant, basically. Okay, so let's look at this example. In the synthesis of ammonia from H2 and N2, then the concentration constant is 9.60 at 300 degrees Celsius. You have to calculate the Kp of this reaction at this temperature. So what are we going to do? We have the N2 plus 3H2 gives us 2 moles of ammonia. That means 1 mole of nitrogen plus 3 moles of hydrogen gives us 2 moles of ammonia. So basically, we are going to have Kc will be equal to NH3 raised to power 2 all over N2 concentration, and then H raised to power 3. So to find the coefficient of the mole ratio, we have 2, right? The coefficient of the product, right? And then minus 1 plus 3, that's for the reactant. You have 2 minus 4, and it gives us minus 2. So the temperature is 300 plus 273. Now 273 is the normal atmospheric temperature, so it's equal to 573 Kelvin. So the gas constant is 0.0821. So and then we have Kc given to us as 9.60. So we're going to multiply it out, and then we have the Kp will be equal to 9.60 times 0.0821 times 573 all raised to power minus 2. We're going to have 9.60 times 4.518, and then our final answer should be something like 4.3379 times 10 raised to power minus 3. Remember, there is no actually any units for this. The concentration constant, right, is greater than 1, then we say that equilibrium rises to the right, and then products are formed. But if it is less than 1, then equilibrium rises to the left, and then it favors the reactants. So reactants are formed in that case. Okay, so the equilibrium constant expression for a reaction written in one direction is the reciprocal written in the reverse direction. So the reciprocal of it is basically what it is. So we have the equilibrium constant of a reaction of nitrogen and oxygen to form nitrogen oxide equals 1 times 10 raised to the power minus 30. Using the information, write the equilibrium constant expression and calculate the equilibrium constant for the reverse reaction. So for the reverse reaction, that's what we're looking for. But for the reaction itself, we said that the Kc is 1 times 10 raised to the power minus 30. So for the reverse, we're going to have 1 over 1 times 10 raised to the power minus 30, and it is 1 times 10 raised to the power 30. All right, let's proceed. We have direction of reactions. So we use reaction quotient, which is the number obtained by substituting reactant and product concentrations at any point during a reaction into an equilibrium constant expression. So this is for the quotient. Basically, we have the product, remember, over what reactant. Basically, that's, and then if Q is equal to K, then we say the system is at equilibrium. So, but when Q is greater than K, the reaction moves from right to left. And then if Q is less than K, we say the reaction moves from left to right. So Q is calculated constant, while K is from experiment. Okay. We have this at 448 degrees Celsius. The equilibrium constant for the reaction, hydrogen plus iodine, gives them hydrogen iodide, right, is 50.5. Predict the direction the reaction will proceed to reach equilibrium if we start with 2 times 10 raised to the power minus 2 moles of hydrogen iodide, and then 1 times 10 raised to the power minus 2 moles of hydrogen, and then 3 times 10 raised to the power minus 2 moles of iodine in a 2-liter container. So thanks for watching. Drop your answer in the comments. See you again.